class 26. We're going to be looking at a very important theorem that has to do with polynomial functions called the factor theorem. And to help us with this factor theorem, we're going to actually learn how to divide polynomials. And there's two methods for dividing polynomials. One is called the long division algorithm. And it really pretty much follows exactly the same process of what you've learned when you did long division. And then there's another method that the book will present to you. I will not require you to learn it. However, some of you might say, ooh, I like this better because it's faster and quicker, but why it works is yet to be determined probably in terms of your own understanding. Whereas I think the long division algorithm you can understand based on what you've already learned. So you will see, listen up if you're writing something. Okay, so that so you won't have this question for yourself later on. You will see two homework problems, number 10 and 11 on tonight's assignment that will present you with a problem. And as part of the problem, it will say, use synthetic division. You don't have to use synthetic division. You can just use your long division algorithm. However, if you would like to do that, that's fine as well. So on a quiz or a test, I always ask you to show work. I don't care which of those methods you use. All I want you to do is to be successful in using them. So whatever works for you is fine with me. Okay, are we clear on that? All right, so let's take a look. Today's preview activities is a little intro into what we're going to be doing today. So I think maybe in like 7 or 8 minutes you should be able to get through this. So just put up your flag when your table's finished, and then we'll continue. The division algorithm, I just want to show you that a lot of you probably, if you went through elementary school in the United States, you've learned the division algorithm pretty much a standard way. However, what you need to realize is it's just an algorithm, it's a process, and there's nothing magic about it, or there's nothing ordained about it. It didn't come down from above. It's the way we have chosen to show you how to do division algorithm. The division algorithm. Just to point out for you, I want to show you what other countries do. If you look at this first country here, which I believe is Japan. Is that Japan? Yeah. Notice that algorithm right here in the light blue looks exactly like ours. However, as you look across, I mean, look at this light pink one here. That looks very different than what we've learned. And this light green one. Okay, so as you can see, different countries have learned different algorithms. I've had students in this class from many different countries. So as I've presented the algorithm as we've learned it, it's been very confusing for them. If you have learned another algorithm, when we make the connection between the long division with numbers, the arithmetic division problem, to the algebraic, I will sit with you and you can show me how you've learned it in whatever way that you've learned it, whether it's a different country or just a different method, and I can make the connection for you. So don't fret, you don't have to like learn something different if you learn the long division algorithm in a different country. So I just wanted to show you this, and the same is true for multiplication as well. Multiplication isn't taught the same way in every country. Okay, so just a little, I guess, mathematical diversity for you. Okay, so everyone, I think, successfully got 71 and 6/11, yes? How do you check your answer? Can someone tell me how they would check this answer, what process you would actually do? I'll be the writer, you be the explainer, and tell me what you would do. Ben? I'm the writer. You need to tell me exactly what to write. Okay, now what? I don't know how to.
You're good. You follow directions very well.
With the line under it. 71 and 6/11 with the line under it. I don't understand. Danielle? 11 times 71, I understand, and that equals 781. Have you ever learned how to multiply by 11 really quickly? It's really cool, right? You're always you put your 1, you put your 7, and then you add these two digits together, 781. All right, so 11 times 71, and then what, Danielle? Plus, I take that answer. I don't write a plus 6 right here, because that's a run-on equal sign, just like you'd be marked off in English for run-on sentences. This is a true statement. You can't put the plus 6 there now and keep the equal sign. So 781 plus 6 is 787. Okay. So you take your, what's this number called? The 11? Not right here. The divisor. It's not a factor because it has a remainder. The divisor, and what's the 71 called? What?
Where you circled it with a factor.
Oh, yes, yes. All right, where I circled it. Sorry. Thank you, Ira, for pointing out. You are correct. It is a factor up here. I'm sorry. What about the 71? Quotient. I heard another word, dividend, which there's only one left. Where's the dividend? Inside the 787 is our dividend. Now, a lot of you are in business. You know that dividends get divided up, right? You're in the business administration transfer program. It's the 787 we're trying to divide up here. That's the dividend. And then what do we call that 6/11ths? The remainder, right? So regardless of whether we're doing arithmetic or algebra, your dividend is equal to your divisor times your quotient plus your remainder. You'll see that later on. Now, one of the real issues that I've seen in probably the last 10 years more than anything else is I've seen people do this long division problem, and why it's critical to write your remainder as the 6 divided by your divisor is a lot of times people will see the remainder of 6, and you know what they do? They do this. They do this. Don't copy this down. They go like that. They just take whatever their remainder is and they put it after the decimal point, as if your divisor was 10, or if it was 0.64, they put as if it was 100 there. The fraction and the decimal are related to whatever the denominator is, which in this case is your divisor. Okay, so be careful. I hope none of you do that, but if you do, just be aware of that. All right, descending order, everybody has that. Again, to factor this, what do you know? Whenever you divide two things, whatever the answer is, the 2x squared plus 3x minus 2 times the x minus 3 will bring you right back to where you started. Notice, what's the degree of my numerator here? What's the degree? 3, right? The highest power you see is 3. What's the degree of my denominator? 1. So when you divide a third degree by a first degree, you get a second degree. Okay. So this is just like saying 12 divided by 2 is 6, and you can check it. You can factor that by saying 6 times 2 is 12. Okay, 6 times 2 is 12. Similarly, you take this answer, the quotient, multiply it by the divisor, and now you need to just factor this little thing, which is 2x minus 1 times x plus 2. So that's completely factored into all of its prime factors. Any questions on any of this before we move along? All right, so let's take a look at this long division algorithm. What I want to do is I want to show you the long division algorithm using our place values. And then I want you to see how it can turn into a polynomial, 2 polynomials being divided. So notice this is the problem you all just worked on in your preview exercise, except for calling it 11, I've made it called 10 plus 1. And instead of calling it 787, I've called it 700 plus 80 plus 7. Okay. Now, Some of you may know that multiplication is repeatedly adding the same number. It's just a shorthand notation. So if I had 3 plus 3 plus 3 plus 3, multiplication is 4 times 3. If I had 4 plus 4 plus 4, it's 3 times 4. Division is just a fast way to repeatedly subtract the same number. That's all division does, is it just groups them into the largest possible groups. So I could sit with the number 787 and subtract 11 and subtract 11 and subtract 11 and subtract 11 and then group it. And I would notice that I could subtract it 70 times and then one more time with that remainder of 6. That's what the algorithm helps us to do, is that repeated subtraction just really quickly, right? But of course, not as quick as a calculator, right? So, okay, so let's take a look at this. What's important is that you always take your largest place value for both your dividend and your divisor, and you say, how many times does 10 go into 700? What would your answer be? 7? 10 goes into 700, Eric? Eric, say it again. 70 times, right? So your answer you want to put above its like place. So you don't put the 70 above the 700, you put the 70 above the 80, because that's the place value. 70 is in the second place from the right, because it's always, we're a base 10 system, so this is 10 to the first, 7 times 10 to the first. This is ones, which would be 7 times 10 to the 0 place if you wanted. This would be like 7 times 10 squared, all right? So now what do? We take 70 and we multiply it by the entire divisor. 70 times 10 plus 1 is 700 plus 70. Now this is the process we go through. I'd like everybody for a minute just to take out some colored pen. So when we have numbers, we have like a 70, what looks like 78, but it's really 780. And underneath we write the 77, and we don't have to worry about signs because we just subtract the numbers. So don't write this quite yet. I'll show you where I want you to use your colored pencil. What we're going to do now is we're subtracting those two numbers. We're subtracting the 70 and the 7. Excuse me, the 700 and the 70. So when you do that, you must drop your parentheses and distribute that negative sign, that subtraction sign, through to both terms. So with your colored pencil, I want you to change the sign of the 700 to subtraction and this to subtraction. You're going to subtract both of them. Having an even if you work with pencil, have a pen with you. If you work with pen, have a pencil. This will help you not make what's called the common mistakes with long division. Now notice you've created this, so this will always be 0. 700 take away 700. And now what do we have left? 80 take away 70, which gives us what? 10. And now we bring down our plus 7. And now the process starts all over. It's a reiterative process. You just keep repeating it over and over. The largest place here, 10 goes into 10 how many times? 1. So we say plus 1. Notice my 1s are above my 1s place. Now I multiply 1 times 10 plus 1 and I get this. And now with my colored pencil, I subtract both of them. And I end up with my remainder of 6. Okay? So the fact that I have a remainder of 6 tells me that 11 is not a factor, of 787, because it has a remainder. The fact that it has a remainder of 6, means it's not a factor. Yeah. Yeah. You're adding those two. You're adding. Subtracting 700 is the same as adding negative 700. So you're subtracting 700 plus 70. That's the same as adding negative 700 plus negative 70. And we just take care of that with a subtraction sign.
So where's
The answer is right here, 0 plus 10, but I don't bother putting the 0 in. I just bring down the 10. What answer, when you say where's the answer? It's okay. Now, the purpose of showing you in the place value form what your long division really does in place value is I want you to turn this same exact problem into an algebra problem. And the way we do that is everywhere you see a 10, you're going to represent it with x. So what would our divisor be now instead of 10 plus 1? Ben, what would it be? X plus 1. Okay, I meant the other Ben, but that's okay. I didn't say Ben O or Ben T. So this is our divisor, x plus 1. Okay. Now, how would I write 700 with tens in it? Well, what could I do? Well, 700 is 7 times 100, which is 7 times 10 squared, which is 7 times x squared. So instead of having a 700 there, I'm going to have 7x squared. Okay, and 80 is 8 times 10, so that's what? 8x, right? So that's a plus 8x. And then 7 is 7. Okay. So this is exactly, I know it looks really different. It's exactly the same division problem, except for now it's algebraic. It's a second degree polynomial divided by a first degree binomial. So your answer has to have what degree? What should my quotient have for a degree? First. Because a first degree times a first degree gives you a second degree. All right. It's just like saying, what do I get when I take hundreds and I divide like 120 and I divide it by 10? You get something in the tens, right? 10 times 10 is 100. All right. So x plus 1, again, you start with your highest degree and you put it into the highest degree of your polynomial here. So x goes into 7x squared. Well, let's see. X goes into 7x squared is the same thing as saying, whoa, my pen is going crazy on me all day today. Yeah, 7x squared divided by x. How many, if I reduce that 7x squared divided by x, what would my answer be? 7x, right? That's like my 70. See over here? It's like my 70. 7 times x, 7 times 10 is 70. So I put my 7x right above my 8x. Now what do? I multiply 7x times x plus 1, and I get 7x squared. Notice these are always identical. Always, these first two here. Plus 7x. Now I have to subtract that. So what do I do to both terms? I change the sign with your colored pencil that you have at your seat. And 7x squared take away 7x squared goes to 0. And 8x take away 7x gives me 1x. And I bring down my next place value, 7. And now I start this all over again. Start with the biggest term here, the biggest power. X goes into x one time. So I put a plus 1 up there, and now I say 1 times x plus 1 is x plus 1. And now I must subtract both of those. So I change the sign of both. There we go. That goes to 0, and my remainder is 6. So that's long division with the problem that we just looked at with arithmetic. Any question on how I went through that process? We're going to do it again, so don't worry. We'll do it a couple of times. Any questions? You had a lot of questions with the arithmetic. Yeah, Victor? The remainder would look like this. Here's your answer, here's your quotient, and the remainder is 6 over x plus 1. Yep, that's the remainder. Okay, so let's take a look at the next problem we have in the class demo. So here's a bigger polynomial to divide. Well, not really. It's still a second degree, 6x squared divided by 2x plus 3. Guess what? You can already factor this. You already can factor this by using your traditional methods. But we'll just go through it with the long division algorithm. The first thing you always want to make sure of, always, is that your dividend is in descending order. What would happen if you didn't have like any x terms and you wanted to do this? Let's suppose it said 6x squared take away 6, but you wanted to do the division algorithm. What would you write underneath your division sign? Just a 0? So suppose
0x.
Yeah. So if you don't have any any of the terms, you have to put a 0 in there. So if it was 6x squared minus 6, before you divide it, you have to put it in descending order, and every single power needs to be represented, every decreasing power, and by putting a 0. Just like if you had the number 106, you would write 1 in the hundreds place, 0 in the tens place, and 6 in the ones place. The same thing is true for long division. So let's do this division. 6x squared plus 5x minus 6 divided by 2x plus 3. So again, you start with your highest degree term here, and your divisor is 2x, and you put it into your highest degree term here, 6x squared. So off on the side, you say 6x squared divided by 2x is 3x. I line my 3x up above my 5x. That's the like place, the like term. Now I multiply 3x times 2x plus 3 with my distributive property, and this is what I get. Now I subtract both terms. Subtract, subtract. That goes to 0. And now I have negative 4x, and I bring down my negative 6. Yep. Oh. And you'll see in a second. Now 2x goes into negative 4x how many times? Negative 2, because off on the side of your paper you're saying negative 4x divided by a positive 2x is a negative 2. My x's cancel, and I just have a negative 2. That goes above my ones place. And negative 2 times 2x plus 3 is negative 4x minus 6. And you're really happy when you see that, because that's identical, right, to what you had above it. And so when you change the signs, you get a nice big fat 0 there, and that tells you that 2x plus 3 is a factor. There's no remainder. So 6x squared plus 5x minus 6 can be factored as 2x plus 3 times 3x minus 2. And you could always check that with your distributive property twice, or what some of you call FOIL. That's how you would check it, just by multiplying it back. Victor?
Maybe I missed it. Why did we change this?
Because you always subtract. When you do this, you're subtracting it. Because you're basically saying what's the largest group of 11s I can get? You tell it, and then you take that group of what you're repeatedly subtracting. So that's why you subtract.
So, in reality, you are subtracting whatever you're getting. So, okay.
You're subtracting.
You can say subtracting your whatever.
How does all this crap relate to what we were doing last Wednesday, right? With all these polynomial graphs and the zeros and why do we have to even like have this tool in our toolbox? Yeah, because with quadratics and linear functions, there's not much work to do to solve a linear function for 0, and you've learned several different techniques for putting a quadratic function, setting it equal to 0. But what do you do with these more complicated cubics and quartics, etc.? Most of the time we have to use technology to estimate the zeros. We can't really use an algebraic technique, but we can learn some algebraic techniques like long division to help us out with some of the small, lesser degree polynomials. So here's an idea. It says, suppose a polynomial function f has zeros. Notice whenever you list zeros, this is a little clue for your project. You just list the values of the zeros. You don't turn them into x-intercepts. I'm not asking you to graph it. So the zeros here are negative 2, 1, and 3. They all have multiplicities of 1, which you could tell from looking at this graph, because at negative 2, 1, and 3, the graph goes directly through, right? It changes sign. Here at negative 2, to the left of negative 2, it was below the x-axis. To the right of negative 2, it's above the x-axis. So it changed sign and went straight through multiplicity of 1. We know that every single polynomial can be factored to look like this. X take away the first 0, x take away the second 0, down to x take away the nth 0, however many zeros it has. This case, we have 3 zeros. So our polynomial would look like this. x take away the first 0, x take away the second 0, and x take away the third 0. Oops, that should be a C. Okay, notice how many factors do you have? 3, right? There they are. And you have powers of 1. So whenever you're trying to determine the degree of a polynomial and it's in completely factored form, you add the exponents. That's the only time you add the exponents to get your original degree. You don't have to multiply that all out to determine that it's an x cubed. Okay? So that's a little clue also for your project. Now, if I wrote this in polynomial form, I know my first term is going to be an x cubed and there's going to be stuff following it. Do I know what the coefficient's going to be? Do I know what sits out here from looking up here at this one? A. Whatever A is in factored form is exactly the same as the leading coefficient. That leading coefficient never changes, whether it's outside all of your factors or whether it's the leading coefficient in your polynomial form. Always the same. So when you get down to this problem in your class activities, what's the leading coefficient here? 2, right? This is polynomial form. The leading coefficient here is a sub 2 is equal to 2. That's your leading coefficient. So when you factor this, that 2's got to sit outside here. It's the same exact leading coefficient. Ben? Yep, because this is second degree. If this had said 2x to the 5th plus a bunch of junk, then it would be a sub 5 is 2. Yep, that's just how we label it. Yep. So we know which term it goes with. All right. So I'm going to sound like a broken record right now, but it's an important broken record because if you know a factor, you know a 0. If you know a 0, you know a factor. So I know that -2 is a 0. So when I go to put it in factored form, I say a times x take away a -2. What does that become when I simplify it? X plus 2. So here's my first factor, x plus 2. My next 0 is 1. When I put it in x minus 1, no need to simplify it, 1. And x minus 3, no need to simplify it, 3. So notice, this is the form of factoring with your zeros. It's always x take away whatever your 0 is. And if your 0 happens to be a negative number, then your sign subtraction changes to addition. Right? So if blank is a factor, if x plus 2 is a factor, then f of what equals 0? A times x plus 2 times x minus 1 times x minus 3. If x plus 2 is a factor, and I set that factor equal to 0, then f of what number is 0? -2, right? Whatever makes this factor a 0, x being -2, makes the whole polynomial equal to 0 because this is multiplication. And anytime one of your factors is 0, the whole thing's got to be 0. So if x minus 1 is a factor, then f of what is 0? 1. Just look at your factor. What makes that 0? If x minus 3 is a factor, then f of 3. Now, it works the other way. If f of -2 is a 0, I know one of the factors of the polynomial, just like that. You tell me a 0, I tell you a factor, x plus 2. Woohoo, this is going to be good. I can look at my graphs and get my factors right out. If f of 1 is 0, x minus 1 is a factor. If f of 3 is a 0, then x minus 3 is a factor. So again, if you know a factor, you know a 0. If you know a 0, you know a factor. So if you have your graph in front of you and all of your zeros happen to be nice integers, you can factor your entire polynomial from looking at the graph and knowing the multiplicities. So here's the big theorem of the day right here. If f of x is a polynomial, and if f of c is a 0 of your polynomial, then x minus d is a factor of f of x. To reverse it, if x minus z is a factor, then f of c is a 0. So let's use that in this next problem here, and then it's going to be time for you to do a bunch of work on your own. So use the factor theorem to solve the equation. All right, use the factor theorem to solve the equation. So you say, given that -2 is a 0 of that polynomial. So if it's a 0, if -2 is a 0, how can the factor theorem help me? What does it tell me? It tells me one of the factors, right? So if -2 is a 0 of this polynomial, then one of the factors by the factor theorem, if -2 is a 0, then x plus 2 is a factor. So I need to solve this equation, folks, right here. Now, if I gave you this equation a little bit ago and I asked you to solve it, you would say, I don't know how to. First of all, it's not quadratic, so you can't use the quadratic formula. It's certainly not linear, and you can't factor this knowing any technique right now, any of the techniques that you know. So all you know right now is if you put a -2 in here and you put -2 in for x, the left side would be 0 and the right side would be 0. So you'd be, well, how am I going to find my other factors? Well, you could graph it. You could graph it and hope that your other factors are nice numbers that you could read right off the graph. Or you could use the factor theorem in long division. You know that if you took this polynomial, 2x cubed minus 3x squared minus 11x plus 6, and you divide it by x plus 2, you will get another polynomial with remainder of what? If x plus 2 is a factor, it divides this evenly. What will the remainder be when I do my division? Right, my answer will be a quadratic. That's right, Ira. What will my remainder be? 0, because if something divides into something evenly, then its remainder is 0. That's what we mean. It's a factor when we say divides evenly. So, and Ira's correct. He knows what to expect on this right side. He knows that the polynomial on the right side, the answer will be second degree because look, you've got a third degree polynomial in your numerator and you're dividing it by a first degree. So you've got to end up with an x squared on the right hand side. So let's do it. And then we'll be able to finish our process here and solve. Let's not lose track of what we were originally asked. We were originally asked to solve the equation for 0. So let's factor it first. So x goes into 2x cubed, 2x squared times. I get 2. I'm going to go a little faster now. So if there's anything you don't understand, let me know. You're probably working away as I am. Minus 7x squared minus 11x. So I get minus 7x. Minus 7x squared minus 14x plus 3x plus 6 plus 3. Oh boy, it looks exactly like it did. Oh, I'm so happy. Minus, nice big 0. So 2x squared minus 7x plus 3. Now we know that 2x cubed minus 3x squared minus 11x plus 6 equals x plus 2 times this polynomial. So let's keep going. I'm going to have to erase some stuff here so I don't lose track of where I am. So let me erase a bunch of stuff right here. So we know that this is equal to x plus 2 times 2x squared minus 7x plus 3 equals 0. So remember what my original question is. Find the solutions to this equation set equal to 0. So if I can factor it, then I know each factor gets set equal to 0 and I have my solution. So I have to factor 2x squared minus 7x plus 3. Oh, good. That's one that I know how to do. So there we go. There's the factorization. So what are my 3 zeros? Well, I know one of them is -2. This one is 1/2, and this one is 3. So my 3 zeros are -2, 1/2, and 3. And if you were working in my math lab, they'd ask you to put that in a solution set like this. Those are the 3 solutions to that equation. Okay, so have fun. You got a lot of activities to do. Should keep you nice and busy. Any requests for music? Who? Jim Brickman. Okay.